Hey, did you hear the news? IPv6 is here. So let's talk about addressing designs. And not only are we going to focus on IPv4, but we'll give particular focus to IPv6. Yeah, I find most students today, they're pretty well versed in how they would design a V4 infrastructure, but they are intrigued and maybe even a little intimidated about the next generation of TCP/IP, and that's version 6. It's a pretty well known fact that with V6 and V4 addressing, we can't just haphazardly approach the dissemination of the address information. There are some tried and true design methodologies to make your network more efficient. And that's really what I want to emphasize. In both the V4 and the V6 world of addressing design, I want to emphasize efficiency. And I want to emphasize optimum performance based on the dissemination of addresses. You see, let me give you a quick example. A lot of times you'll hear people go, oh, all right, V4 design, I know what Anthony's going to talk about. He's going to talk about taking a really big routing table and maybe like summarizing that routing table when he sends it over to another router so there are fewer routes in that routing table. And they immediately think that, okay, this will reduce the size of the routing table and therefore take up less RAM on the routing devices. Well, sure, that's true, but I say that's probably one of the least reasons we would want to summarize routes. I mean, after all, our routers today have more and more memory and are capable of much more horsepower. Now, what's more powerful about route summarization is what we call convergence domain reduction. Yeah, convergence domain reduction, meaning when there is a change in one part of the network, that does not need to be communicated to another part of the network. This is another huge benefit of summarization, and I would argue this is much bigger of a deal than reduced routing tables. So, as we go through these tried and true methodologies for designing V4 and V6 addresses, we'll really focus on operational efficiency. Now, hasn't it been a theme as we've moved throughout this CBT Nugget series that we need a plan? Yeah, of course. We definitely need a plan. And with addressing, that is no different. Here's four big questions in order that we're going to want to ask in order to come up with a perfect addressing plan, or as near perfect as we can make it, for an organization. What are the locations that we're going to be accommodating? That's right, let's get all of those topology documents that we drafted maybe for other areas of the network design. We're going to need those to go ahead and list out the locations we're accommodating. What is the number of devices that we need to accommodate in the addressing plan? And remember that this is a bring your own device type of world. So let's really brainstorm on the devices that we're going to need to accommodate with addressing in a particular location. What are the special requirements of some of these locations? Here, what we're primarily talking about is what devices will have static addresses versus what devices will have dynamically DHCP assigned addresses. And then the big one, what are the exact subnet sizes that we are going to utilize in the various locations? Maybe for a particular location, we realize that we are going to have a 48 port switch. And that 48 port switch is going to accommodate the end systems in that particular location. So we go ahead and we assign a subnet of 64 addresses. That's the closest power of 2 number to accommodate the 48 port device that we have in that particular section of the network. So when it comes to the addressing plan, let's remember these 4 important questions. Now, you know what word we've used a lot in this Nugget series? Hierarchy. And I think I shared with you that I was so proud of myself when I could say hierarchical. It took me a long time to be able to say that. Well, listen, hierarchy is hugely important when it comes to addressing. Yeah, what you're going to do is, let's say you have this building. Okay, we'll say building one. You're going to think about how, maybe there's one subnet in here, and then you have building two, and there's a second subnet utilized here. You're going to want to think about aggregating this address space, summarizing this address space as we go to a different area. Yeah, maybe there is two other buildings, building three, and it's got addressing that we don't aggregate, but then there's building four and building five, and we are going to aggregate these addresses here. And then it goes up in the hierarchy and we aggregate right here. Okay, and we aggregate these, and then we have the core of the network. So you see what's happening. We're having multiple levels of aggregation, and this creates a nice hierarchy. Now, what does this do for us? Well, I've already alluded to it in our introduction that it's going to reduce convergence domains, but I want to elaborate on that for you next. You see, it results in what I call the joys of summarization. Look at this simple example. So we've got subnets in this area of the network of 10, 10, 10, 10, 10, 20, 10, 10, 30, all using a 24-bit mask. We make sure we don't have any discontiguous subnets out there, and we say, all right, look, we're going to summarize all of that to 10, 10, 00/16. So the number one benefit everybody thinks about is, yes, smaller routing tables. And let's list that. Okay, smaller routing tables, the SRT acronym that's often overused. All right, so smaller routing tables inside this other area of the network. Awesome, great. But that is not the greatest benefit. Let's talk about the second benefit. When one of these things fails, when there's some kind of a change, notice we do not have to do anything with this particular update. So we're reducing update traffic. What is that doing? Second benefit, we are saving on bandwidth. Sure, there's less bandwidth for routing processes, but I would say, especially with the optimal, real advanced routing protocols we use today, that this is still not the greatest benefit. No, the greatest benefit, our third great benefit here, it is the CPU from convergence. Yeah, let's talk about that. So let's say we're doing OSPF. OSPF in here has to recalculate, and there's a loss of a route. So everything in this particular OSPF area, for example, there are indeed shortest path first calculations that happen as a result of the loss of that route, and there's CPU being consumed. But look at this happy area over here, because nothing changes with the summarized prefix. This area is shielded from the CPU load that this convergence is going to cause. So what do I like to refer to this third benefit as? Well, I said it earlier, it is convergence domain reduction. Yep, convergence domain reduction. We are making the convergence domain, all of the devices that need to converge to the loss of a prefix, we're making that overall domain smaller. And the smaller that domain is, the more efficient our layer 3 architecture. Now, the last thing I want to talk to you about here in the area of v4 design for addressing is assignment and resolution issues. And guess what? It's a decision that we're going to be making on dynamic versus static for both of these. For instance, we have to design what devices will be dynamically assigned address information. And it's the DHCP service that we would rely on for that. What about static assignment? Well, that will be a manual input of the addressing information, and typically that's done on key servers within the organization. What about resolution? Same thing. It's going to be dynamic or static. The dynamic methodology being DNS, the static methodology being a manual creation of host name to IP address mappings. There are going to be times when static, believe it or not, static methodologies are appropriate in part of your IPv4 addressing design. So enough about V4 addressing designing. I mean, for many of you, you were thinking, I knew all of that, Anthony. Thank you very much. Well, let's move to the future then, where we probably aren't going to be as familiar. Let's talk about IPv6 addressing design issues, and let's start with a review of the IPv6 address. It is indeed 128 bits in length. To represent something that huge, we're going to revert to using hexadecimal like we used to in Novell environments. We're going to use hexadecimal for the addressing. Now, there's a couple of tricks that you want to know with the addressing. First of all, let's just quickly review. Each of these characters is a hex character, and each of those is going to represent 4 bits. So we've got 8 16-bit sections that make up an IPv6 address. Now, notice the address is pretty long and pretty ugly, even though it's in this efficient hex representation. So there are 3 tricks I want you to master. Trick number 1 is the fact that the hex is case insensitive. That's right. You can go ahead and put the hex, F or the A. You can do it in upper and lower case. The Cisco device is not going to care. Okay, good to know. The second trick is about leading zeros. We can go ahead and eliminate all of the leading zeros in an address. So I can go ahead and write that address as 2030:0:9C:0:876A:130B. Oh, nice. That shortened it up a bit. All of the leading zeros can be trimmed. And then the third one, we can use : to represent all 0 fields that are successive. In other words, right here, we've got 2 fields that are nothing but 0. So we could do this: 2030:9CA:876A:130B. So that is the most succinct way we can represent this big address up here. This trick number 3, the : trick, can only be done once in an address. So please keep that in mind. That trick can only be implemented once in an IPv6 address. Now, you may have heard a rumor that in IPv6, broadcasts are dead, and I'm here to confirm it. That's right. It's kind of like Elvis death confirmation here, I guess. Yeah, the death of the broadcast is indeed true. But this troubles you, I'm sure, because what happens in the case where we do truly need to send a particular frame to everyone? Well, the good news is we do have multicast for that purpose. Let's just quickly review this. The sending of a frame to one system, yeah, this is handled by unicast. This is going to be how most of our communications go, and this is very similar to the concept of an IPv4 unicast. Multicast is sending to a group, and that's how we can completely eliminate broadcasting in IPv4. You see, when a device comes online in a v6 environment, it will join the all nodes multicast group. this all nodes multicast group will enable the equivalent of a broadcast anytime we need to send a packet to all nodes. Pretty clever. And then there's Anycast. What's the deal with Anycast? Well, with Anycast, let's say we have these servers down here. What we can do is we can assign the exact same IPv6 address. I'll call it address X. We assign this exact address to all of those systems. Notice this is a unicast address. We're just assigning that exact same unicast address to all of the devices. Now what will happen is a local router will decide to which of these systems it sends traffic. You can program the router with an algorithm to go ahead and disseminate traffic to those systems that are all assigned the same Anycast address. So this is a really clever way in which to implement a load sharing approach. So in IPv6, no more broadcasting, but we do have unicasting, multicasting, and anycasting. Now let's go ahead and examine this. Let's bring this to life at a Cisco router, shall we? So what I'm going to do is I'm going to go ahead and say configure terminal, and I'll go into a fast Ethernet 0/0 interface, and I'll issue the command IPv6, and we'll drop in a v6 IP address. We'll go ahead and use that shortcut trick, and this will be an address in the EUI64 format. What this means is the first 64 bits I assign, and that's the network portion of the address. The last 64 bits, the machine can go ahead and automatically create the host portion of that address. This is the recommended method in IPv6 worlds of setting up the addressing. We do the network portion, we have the host portion created automatically for us. So we have just given an IPv6 address to our router. By the way, notice that we didn't have to do anything fancy in order to do this. I mean, this Cisco router was ready for IPv6 address assignment right out of the box. Now, if I do a show IPv6 interface FA0/0, what we see is, sure enough, we have a global unicast address now. Notice the host portion was indeed created for us automatically. And look at this. We have joined a multicast group address. And the multicast group address that we have joined is the all nodes multicast IPv6 address of FF02::1. If I go to this router and I say IPv6 unicast-routing, and we turn on routing capabilities on this device, and then we rerun the show IPv6 interface command, we see now we've joined another multicast group address, FF02::2, and this is the all routers IPv6 multicast address group. So here we can see these addresses coming to life at a router's command line. Now, something that happens with IPv6 that is quite different from IPv4 is the automatic creation of a link local address when IPv6 hits an interface. I want you to think of Microsoft's automatic private IP addressing here. Know how Microsoft systems will do this? If this machine fails to get a DHCP address, right? And then this machine next to it fails to get the DHCP address, they will automatically configure each other with an address in the 169 space, so at least they can communicate with each other. That type of concept is what we have with the IPv6 link local address, except it's not like a a bailout solution like we have with the automatic private IP addressing. It is by design, and it has a whole bunch of different uses. I bet you want one example. All right, sure. A PC comes up on the network and it does not have any address information. It will be able to communicate with its local router because, sure enough, both of these devices automatically get link local addresses. Now it can say out on the network, are there any routers around? The router can say, yeah, I'm right here. And by the way, here's your network prefix. Now this machine can go ahead and give itself an IPv6 address once it gets its network prefix. This is called address auto configuration. Yeah, and it's why we can completely, if we wanted to, eliminate DHCP from the addressing equation in an IPv6 world. How awesome. So the link local address, it's going to have a lot of different purposes. It's like the Swiss Army knife when it comes to devices being able to communicate automatically in an IPv6 world. Let's bring that to life at the command line as well, shall we? So here we are back on that router where we configured the IPv6 address. And remember, here we can see the global IPv6 address that we configured. Remember, we configured the first 64 bits, and the machine, thanks to the EUI64 process, automatically configured the last 64 bits. But what about a link local address? Ah, yes, there was indeed a link local address that was automatically configured on the interface. Notice you can easily tell a link local address because that address will start FE80. Yeah, FE80 reserved for the link local addresses. Now, what's the deal with all these addresses, by the way? Are they from Tennessee in the United States? No, they're tentative. And the reason why they're tentative is because this interface is down. So once the interface fully comes up, all of these addresses will no longer be considered tentative. What about subnetting in an IPv6 world? How will that work? Well, how the standards makers believe we should go about this is simple. They say, look, go ahead and use the EUI 64 format to have machines automatically configure their own host portion. And then I said the network portion would be 64 bits, right? Well, yeah, technically it's the first 48 bits, and the IETF says that we should go ahead and use the 16 bits in between these 48 bits and these 64 bits, and these 16 bits should be used for subnetting. So if you get one of these global unicast addresses from the Internet Assigned Numbering Authority, you're probably wondering, well, how many subnets could I create with this one address space? Well, I don't know about you, but I think I'm going to need the scientific calculator for this one. So let's see. We have 2 raised to the 16th power. Oh my goodness. Is IPv6 scalable? You bet it is. We can create 65,536 subnets with this one slice of the address space thanks to 16 bits earmarked for the creation of subnets. So we have an extremely scalable protocol here with the IPv6 suite. Now, what about address assignment? Well, as far as statically assigning addresses to devices, this would work the same way it does in v4. We just have to be very careful not to make typos as we are manually assigning the address information out there on the network. But when it comes to dynamic methodologies, we can go ahead and emulate exactly what we do in v4. We can do DHCP v6 and we can statefully give out address information. So we can emulate a v4 environment there. I'll go ahead and put v4 right here so we realize this is the same as v4. Now, some uniqueness. Sure, the three methods I have here, 1, 2, 3, would be very unique from a v4 world, right? Number one, we remember the link local. Yeah, that link local address that gets automatically created for communicating just on the local link. And then there's the stateless auto configuration that we talked about earlier. Pretty cool. But the issue with auto configuration is, sure, the local device can get its own IP address. That's great. But what about its DNS servers? What about its default gateway? What about its domain name? What about all of the goodies that would go along with an IP address? Well, that's the job in v6 of what we call stateless DHCP. You see, you let the devices auto-configure their addresses, but then you use DHCP for everything else. Default gateway assignments, DNS assignments, domain name assignments, etc. So, more differences in the wonderful world of IPv6. What about name resolution, you might ask? Well, nothing really new to report here. We can do this statically or dynamically. With static, we're going to do manual host type entries in IPv6. With the dynamic, we're going to do none other than DNS. So very little changes from a name resolution standpoint in IPv6. But you know what one of the most complex areas are when we talk about v6? It's how in the world do we transition? Yeah, it's not like we can just make a phone call and say, hey, the internet's going to be down for 45 minutes next Tuesday as we cut over. That's not possible. So you know what we have? Thank goodness. We have the ability to do what's called dual stack. Now, dual stack is nothing new at all. In fact, I dealt with dual stack in a Microsoft/Novell environment years ago. Remember, you'd have Microsoft running IP, and that would be sitting on an interface right next to IPX of Novell. So dual stack is nothing new. But in this v6 world, it just means that we're going to have the v4 stack sitting right next to the v6 stack. So now that you have devices that can run both v4 and v6, particularly routers, we get the next transition mechanism, and that is tunneling. Of course, what we're going to do is we're going to go ahead, and by the way, there's one L in tunneling, so don't do what I do. Just see what's there on screen. So with tunneling, what we're going to do is we're going to have, let's say, a v6 only area over here, and then we're going to have a router, and then we'll have our internet, v4 only, and then we'll have a router, and then we'll have another v6 only pocket. What do? Yeah, of course, we create a tunnel between these two devices. And what we're doing is we're putting the v6 packet inside of a v4 for transmission over this v4 only segment. Wow, it's simple. It's simple. And guess what? There's many types of tunnels. There's manual tunnels. There's automatic tunnels. There's even what we call semi-automatic titles. And suddenly this sounds like some kind of a seminar on guns. But there are many transition mechanisms because transitioning is going to be so necessary. In fact, we shouldn't in our lifetimes see the end of v4. No, pockets of v4 will get smaller and smaller, but they'll never be completely eliminated, at least in our lifetime. Now, the third thing that we could do is we could translate. This won't be all that popular, but we could do something like, we could do what's called network address translation, protocol translation. And what you do here is you take the v4 address and you translate it to a v6 address on the NatPT device. Lots of instructors don't like to even bring up this technology because they are afraid they're going to confuse their students who think that NAT lives on in a v6 world. NAT does not, I repeat, NAT does not live on in a v6 world. No. What we have potentially in a v6 world is NAT PT, which is different from NAT. That's where we convert one address into the other address. So, transition mechanisms, dual stack gives the capability for many different types of tunnels, and what won't be as popular is translating a v4 address into a v6 or vice versa, translating a v6 into a v4. So I'm sure you're not surprised. When it comes to deploying IPv6 in a v4 world, we've got options thanks to all the transition mechanisms. Sure, think about it. One option is to just completely remain dual stack. Yeah, you go ahead and you just overlay v6 right on top of your v4 world, and you have both protocols operating, and then, gradually you can start removing the v4. Another way to go is the hybrid approach. With the hybrid approach, we're going to go ahead and configure, like I described, tunnels. So here's router 1, router 2, here's v6 only, here's v6 only, here's v4 only, and we construct a tunnel for the movement of the v6 traffic across that v4 only location. The service block approach, well, with the service block, we call upon something called isotap tunnels. Yeah, so what happens here is you've got this v6 area, and then you've got this v4 only area, and you've got one router here, let's call it router 7, that is dual stack. And sure enough, with isotap, what happens is a device comes online and is able to dynamically create a v6 tunnel to this router that's dual stack in order for it to communicate into the v6 world. So an isotap tunnel is one of the many types of dynamic tunnels that can be created. Yeah, so it's for within a site only, and it's for the automatic tunneling of devices in that v4 only world for allowing them to communicate with the v6 environment. Pretty cool. So, IPv6. Boy, we've taken a much more in-depth look at this than we did with v4, and that's for obvious good reason for many of us watching this presentation, yeah, we're probably not going to be as familiar with v6 for obvious reasons. So in this nugget, we took a look at IPv4 and IPv6 address design issues. And we address those issues with great tips and tricks, including a rather in-depth tour of v6 and the wonderful world of addressing there. Well, I hope this has been informative for you, and I'd like to thank you for viewing.